Namaste to all and welcome back to my class. Today I'll be starting with Unit 3 Electrochemistry. It is a well-known fact that energy manifests itself in different forms which are interconvertible into one another. Among different forms of energy, the electrical energy plays a very significant role in our daily life. Many chemical transformations and industrial processes are based on electrical energy and its relationship with chemical energy. There are a large number of spontaneous redox reaction which forms the basis of production of electrical energy. The device in which such chemical processes are carried out is called electrochemical cell or galvanic cell. The branch of chemistry which deals with the study of relationship between electrical energy and chemical energy and the interconversion of one form of energy into another is called electrochemistry. In this unit, we shall focus on the study of some aspects of electrochemical cells. We'll be learning what is an electrochemical cell, that is a galvanic cell, a Daniell cell, what is EMF, the meaning of electrode potential, the conductance and its measurements, etc. So first, before going into galvanic cells, we should know what is a redox reaction. We have learned redox reaction in the 11th standard. That is, chemical reactions involving oxidation and reduction process are called redox reactions. Oxidation may be defined as a process in which a species means atom, molecule or ion, increases the oxidation number by losing one or more of electrons. The substance undergoing oxidation is called the reducing agent. And what is reduction? Reduction is a process in which the species, that is atom, molecule or ion, decreases the oxidation number by gaining one or more electrons. The species undergoing reduction is called the oxidizing agent. So neither oxidation nor reduction can take place alone. They are complementary process and occur side by side. So redox reaction can thus be termed as the chemical reaction involving transference of electrons from the reducing agent to the oxidizing agent. So the definition is given here. What is electrochemistry? The study of production of electrical energy from chemical reactions and the use of electrical energy to bring about a spontaneous chemical change. Galvanic cells. So first we are focusing on galvanic cells. It is an electrochemical cell, that converts chemical energy of a spontaneous redox reaction into electrical energy. Earlier I had mentioned electrolysis. Electrolysis is converting the electrical energy into chemical energy. So that we have learnt last year. Even the galvanic cell also we have learnt last year. So the galvanic cell, the device in which, once again repeating it, the device in which the chemical energy is converted into electrical energy is called a galvanic cell. It's named after the scientist Galvani, or electrochemical cell or voltaic cell, also named after the scientist Alessandro Volta. So in a galvanic cell, a redox reaction is carried out in an indirect manner. Indirect manner means there are two types of redox reaction that you have learned last year. When the redox reactions are taking place in one vessel, it is called a direct redox reaction. When it is taking place in two different vessels, it's called an indirect redox reaction. So this is an example of an indirect redox reaction, and the decrease in free energy. It is free energy. There is a decrease in free energy during the process is made to appear as electrical energy. An indirect redox reaction is such that reduction and oxidation, as I've told you earlier, takes place in two different vessels. So we'll go to the diagram of the galvanic cell. The Daniell cell or the galvanic cell. As you can see here, this is the diagram of the galvanic cell. There is a zinc strip, a zinc anode which is dipped in zinc nitrate solution. What we have learned is zinc sulfate solution, can also be zinc nitrate also. So zinc nitrate solution, and here you can see the other side, the right hand side, a copper rod. That is copper rod, that is a cathode, is dipped in copper nitrate solution, which is taken in two separate beakers. The two rods which act as electrodes are connected by conducting wires through a voltmeter. You can see there. The two solutions are joined by an inverted U-tube known as the salt bridge. The U-tube is filled with a solution of some electrolytes such as KCl, potassium nitrate or ammonium chloride, to which gelatin or agar-agar has been added to convert it into a semi-solid paste. The deflection in the voltmeter indicates that there is a potential difference between the two electrodes. It has been found that the conventional current flows through the outer circuit from copper to zinc strip. So current is flowing in the opposite direction to that of the flow of electrons. Electrons flows from zinc to copper. So the conventional current flow is from copper to zinc. The electrode at which oxidation occurs is the anode, and that at which reduction occurs is the cathode. So in this cell, the zinc rod is the anode and copper rod is the cathode. Due to the oxidation process, that oxidation takes place at the anode. So that becomes a source of electrons. The zinc undergoes oxidation, it becomes a source of electrons and hence acquires a negative charge in the cell. Similarly, due to reduction process occurring at the cathode, it acquires, because it gains electrons, so it acquires positive charge and becomes a receiver of electrons. Thus, in the electrochemical cell, is very important, anode electrode acts as the negative terminal. Once again, why? Because it is a source of electron, because oxidation is taking place in that side, and cathode electrode acts as a positive terminal. So here you can see a salt bridge also in the center, as I had explained earlier. What is the function of a salt bridge? So the electrolyte that you're taking, there's a condition, the electrolyte that you're taking that is mixed with agar-agar or gelatin, that electrolyte should not react chemically with the solution in either of the compartment. It should not react, it should be chemically inert. It does not interfere with the net cell reaction. That is, these electrolytes should not interfere with the total net reaction. And what is the function of this salt? What is the purpose of fitting this salt bridge? The first function, which you have learned last year, it allows the flow of current by completing the circuit. Second function is it maintains electrical neutrality. Now, how does it allow the flow of current? How does it maintain electrical neutrality? Which I'm going to explain now. The transference of electrons from anode to cathode leads to a net positive charge around the anode. Why? Because when zinc is undergoing oxidation, zinc gets converted to Zn2+. As a result, the Zn2+ concentration increases on the left side, so there is an increase in the positive charge. This increase in positive charge around the anode will prevent the electrons to flow out from it. Because there is greater positive charge, Zn2+ ions have been formed, so it will attract the electrons. It will prevent the flow of electrons, and hence the reaction would stop. Similarly, in the other side also, as the copper is undergoing Cu2+ will gain electrons to form copper. There is an increase in the negative ions in the other compartment. So as a result, it will prevent the attraction of electrons. The inflow of electrons into the copper electrode will stop. The reaction would thus stop, and then no current will flow through it. It is at this time that the salt bridge comes to the aid and restores the electroneutrality of the solution, the two compartments. It contains, as we have learned, it contains an inert electrolyte which is not involved in the electrolytic solutions. The anions of the electrolyte in the salt bridge migrate to the anodic compartment. Why? Because there the positive charge has increased. So automatically from the salt bridge, inside the salt bridge, the negative part, the anions will move or migrate to the anodic compartment, and the cations to the cathodic compartment, because in the cathodic compartment there is an increase in the negative charge. So to restore the electroneutrality, the cations will flow into the cathodic compartment. Thus, the salt bridge prevents the accumulation of charges and maintains the flow of current. So let us go through it once again. The galvanic cell consists of two half cells, the oxidation half cell or the anode, and the reduction half cell or the cathode. In the Daniell cell, zinc is the anode and copper is the cathode. And the reaction, as we had mentioned, here zinc is undergoing oxidation, so zinc gets converted to Zn2+. Cu2+ undergoes reduction. Reduction means gaining of electrons, so Cu2+ gains electrons to form Cu. So here it is written what I have told earlier, Zn2 plus 2 electrons, oxidation half cell, because electrons are lost by the zinc electrode. Cu2 plus on this side gains electrons, undergoes reduction. So reduction half cell because electrons are gained by copper electrode. The next part that we are going to learn is the electrode potential. So what that also we have learned in the 11th standard. What do you mean by electrode potential? That is when a strip of metal is brought in contact with the solution of its own ions, say Mn plus, the charge is N plus. So it has two tendencies. Consider a metal, capital M. You can imagine capital M, a metal is brought in contact. The strip of the metal is brought in contact with its own ions. It's Mn plus. The charge is N plus. It can be any charge. There are two tendencies. What are they? First one is tendency of oxidation. Second one is it can undergo reduction also. That is, metal ions may lose, tendency of oxidation means metal ions may lose electrons to form Mn plus ions in solution. In doing so, the metal strip develops a negative charge. Why? Because it is losing electrons. Because of the accumulation of electrons released, it acquires a negative charge. The solution at the same time will develop a positive charge due to the formation of positive ions, because it is getting converted to Mn plus ions, and in the solution the concentration of Mn plus ions increases. The solution will acquire a positive charge. So the oxidation process does not continue for long. After some time an equilibrium will be attained. That is, M will get converted to Mn plus N electrons. So this they will attain, that is, rate of the forward reaction and rate of the backward reaction will be same, and an equilibrium will be attained. So this is one condition, one tendency of oxidation. So second tendency would be the tendency of reduction. So either the metal will have a tendency of oxidation, or it can undergo reduction also. So second case, tendency of reduction, the metal ions in the solution may gain electrons from the strip and get reduced and deposited on the strip as atoms. So in doing this, the strip will acquire positive charge, because Mn plus from the solution is accepting electrons, and that there is a decrease in the concentration of Mn plus ions. It will get deposited on the metal, will get deposited on the electrode. So a positive charge, it will acquire a positive charge, and the solution, because of the decrease in concentration of positive ions, the solution will develop a negative charge due to the decrease in concentration of positive ions. Here also the Mn plus ions is accepting N electrons to form M. Here also an equilibrium is attained. So once again repeating it, when a metal strip is brought in contact with its own ions, there are two tendencies, either oxidation or reduction. In either cases, what we have found is the equilibrium leads to a separation of charges. Because of this equilibrium, the rod and its solution, there will be separation of charges, and this results into a potential difference being developed between the metal strip and its solution. The net charge separation, and hence the potential difference at equilibrium, depends upon the nature of the metal and its ion, the concentration of the ions in the solution, and the temperature, which we'll be learning it later on. The electrical potential difference set up between the metal and its solution is known as half cell electrode potential. This is called the half cell electrode potential. That is, it is simply a measure of the tendency of the electrode in the half cell to lose or gain electrons. That is, if it is reduction potential, means it is tendency to gain electrons. If it is oxidation potential, means it is tendency to lose electrons, and they are numerically equal, but they will have opposite signs. That is, nowadays, according to the present conventions, the half reactions are always written as reduction half reactions, and their potentials are expressed by reduction potentials. And reduction potentials of an electrode generally increases with the increase in concentration of the ions and decreases with the decrease in concentration of the ions in the electrolyte. And one particular point to be noted, reduction potential of electrode, when the concentration of the ions in the solution is 1 mole per liter. If you are taking the concentration of the ions as 1 mole per liter, and the temperature is taken as 298 Kelvin, then that reduction potential is called the standard reduction potential. And it is actually represented as E naught, and subscript would be RED, reduction. If it is oxidation, is OXI. That is how it is written. So much details are not shown here, and that is the reason why I have explained earlier itself. So repeating it once again, electrode potential difference developed in a half cell between an electrode and electrolyte containing the ions of the electrode. I had explained all the details earlier. Standard electrode potential also I had mentioned. The potential difference developed in a half cell between an electrode and an electrolyte when the concentration of all the species is being unity. That is when the concentration of the ions is 1 mole per liter and the temperature is 298 Kelvin. That temperature is really important. Now, next is cell potential or EMF of a cell. What is it? As we have learnt earlier, the electrochemical cell consists of 2 half cells. That is, we saw in the galvanic cell, there are 2 half cells, the oxidation half cell and the reduction half cell. The oxidation takes place in the oxidation half cell and reduction takes place in the reduction half cell. The oxidation part, the zinc is the anode dipped in its solution, and the reduction part, copper was taken, which is dipped in its solution of copper nitrate. It can be copper sulfate or zinc sulfate also. The electrodes in these half cells have different electrode potential. When the circuit is completed, that is when you are connecting it, when the circuit is completed, the loss of electrons occurs at the electrode having lower reduction potential, because the one having higher reduction potential will have a tendency for reduction, and then the one having lower reduction potential will have a tendency for oxidation when these two are connected. So flow of electrons takes place from that electrode having lower reduction potential, that is zinc, whereas the gain of electrons occur at the electrode having higher reduction potential. The difference in the electrode potential of the 2 electrodes of the cell is termed as electromotive cell, or in short it is EMF or cell voltage. So EMF of a cell is defined as a potential difference between the 2 terminals of the cell when no current is drawn from it. This is the actual definition of EMF. So potential, what is EMF? Once again repeating, potential difference between the 2 electrodes in the galvanic cell. So E cell, the one having higher reduction potential, is the one that is in the right side. And the one having lower reduction potential would be E left. So it is the electrode potential, reduction potential, that is cathode's part minus the anode, because the cathode is having the higher reduction potential. By convention, anode is at the left and cathode is at the right. So E cell, you can write it as E right is the E cathode and E left is the E anode. So EMF of a cell is E cathode, that is reduction potential or higher reduction potential minus the lower reduction potential, that is of the anode. Now, how can we represent a galvanic cell? So here there is an equation given. Consider the equation: copper plus 2Ag plus, that is the ionic state there, which is not shown here. It is 2Ag plus, gives Cu2 plus 2Ag. Now the anode part, as you can see here, Cu, the solid, is getting converted to Cu2 plus. So how is this happening? Because copper is losing 2 electrons to form Cu2 plus. So oxidation is taking place by copper, and Ag plus on the reactant side is gaining 1 electron. Actually, Ag plus will gain 1 electron to form Ag, but the number of electrons has to be made equal. So here it is 2 electrons, so they multiply the second part also into 2, and that is how we are getting 2Ag plus 2 electrons forms 2Ag. So we are splitting this one equation into 2, the oxidation half reaction and the reduction half reaction. So the cell representation also we have learned last year. Always the left, that is easy to remember, is LOAN, lone. L for left. In the left side, O for oxidation. That's left side, oxidation takes place. LOA, left side oxidation takes place, and that is the anode, and N for the negative terminal. The anode constitutes the negative terminal. So on the left side we always write the anode. This is how we represent the galvanic cell. Left side, write the anode electrode, that is first the solid form, and then the second step is the ionized form. First is the unionized form. The second one is the ionized form. Cu/Cu2+. Usually put a slash and not a comma. Draw two vertical lines. After that, we'll draw two vertical lines to represent the salt bridge. And on the right side, we write the cathodic part. So cathodic part, what is happening? The ions are gaining electrons to form, get converted to solid form. So first we write the ionized form, that is Ag plus. And then finally on the extreme right, we write the cathode, that is unionized form. So once again, the cell representation in the left side, it is the anode, and anode first we write the unionized form, that is copper is losing electrons to form Cu2+. So this is how we write copper is losing electrons to form Cu2+. We have to write if the concentration is given in the question, the concentration also has to be written. Then the two vertical lines which represent the salt bridge, and then the cathode part, it is the ionized form, putting a slash and Ag. And one very important point to remember is we need not write the coefficients in the balanced equation. The balanced equation, it is 2Ag, that need not be represented. Without that only we can represent the galvanic cell. So the next very important point or part is the standard hydrogen electron, SHE, or the normal hydrogen electrode. We have learned what is electrode potential. The absolute value of electrode potential of an electrode cannot be determined because a half cell by itself cannot cause movement of charges. And why is it so? It is because that once equilibrium is reached between the electrode and the solution in a half cell, no further displacement of charges can occur unless and until it is connected to another half cell with a different electrode potential. So if you're taking a zinc and zinc sulfate solution, that half cell's electrode potential you cannot find out, because after the displacement of charges, the flow will not take place. So it has to be connected with another half cell which has different electrode potential. Only then the electron will start flowing. So this difficulty has been overcome by finding the electrode potentials of various electrodes relative to a reference electrode whose electrode potential is arbitrarily fixed. And the common reference electrode used for this purpose is the standard hydrogen electrode, whose electrode potential is taken to be 0. The standard hydrogen electrode potential is taken as 0. So all the half cell potentials, electrode potential, are determined by connecting it with the standard hydrogen electrode. And when it is when you are connecting a half cell, SHE can act as an electrode, also can act as a cathode also, and this we can easily find out from the potentiometer or the voltmeter, and it is in this way that we can calculate the electrode potentials of half cell. So before going into the calculation, let us find out what is what is the working of a standard hydrogen electrode. As you can see here, the standard hydrogen electrode consists of a platinum wire. You can see the platinum wire there, sealed in a glass tube. It is sealed in a glass tube and carrying a platinum foil at one end. It has a platinum foil, you can say a brown part, a foil at one end. The platinum foil is coated with finely divided platinum. This electrode is placed in a beaker containing an aqueous solution of some acid having H plus ions, which is taken as unity. There is 1 molar HCl solution is taken, and hydrogen gas at 1 bar pressure is continuously bubbled to the solution at a temperature of 298 Kelvin. That is, this is taken in standard temperature and pressure conditions. The oxidation and reduction in the SHE takes place at the platinum foil. That is, when SHE acts as an anode, oxidation will take place. That is, hydrogen gives 2H plus 2 electrons. And when SHE acts as a cathode, 2 H plus ions, that H plus ions will gain 2 electrons to form H2. So this is how the oxidation reduction takes place. The electrode potentials of other electrodes are determined by coupling them with SHE. The electrode potential of an electrode determined relative to the standard hydrogen electrode under standard conditions is called the standard electrode potential, and it is represented as E naught. That is, when you find the naught there, means this is under standard conditions. So we can see here what is SHE is used to measure the electrode potential of the half cell. It consists of a platinum electrode coated with platinum black. platinum electrode is dipped in an acidic solution and hydrogen is bubbled. The conditions I mentioned earlier. There is 1 molar H plus ions that is taken. The concentration of H plus ions is acidic and H2 is maintained to be unity. That is, it is passed through 1 bar pressure. When SHE is used as a cathode, that is when SHE on coupling with another half cell, when SHE acts as a cathode, E cell is E cathode minus E anode. So E cathode is taken as 0, 0 minus E anode, and so you get the values minus E anode. Similarly, when SHE is used as an anode, then you know the EMF is equal to E cathode minus E anode. So E anode, when this acts as an anode, this is taken as 0, and EMF you can easily calculate, and so E cell would be equal to E cathode. Now I can explain. The explanation is not here in the in this written part, so I can explain this how we can calculate this. That is, in order to determine the standard, I am explaining this part. That is when NHE is used as an cathode and an anode. The explanation part is what I am going to explain. That is, in order to determine the standard electrode potential of an electrode, the electrode in standard conditions is connected to a standard hydrogen electrode to constitute a cell. If the electrode forms the negative terminal of the cell, it is allotted negative value of electrode potential, and if it forms a positive terminal of the cell, it is allotted a positive value of electrode potential. The potential difference between the electrodes is determined with the help of a potentiometer. So you can find out the potential difference with the help of a potentiometer. At the same time, the direction of flow of conventional current in the external circuit is also noticed with the help of galvanometer. So the conventional current can be observed from the galvanometer, and so the electrons flow will be in the opposite direction. That is, conventional current is from cathode to anode. The flow of electrons is from anode to cathode. Remember that. So we can, after coupling it from the galvanometer, we can find out which is the anode and which is the cathode. And through the potentiometer, we can find out the difference. The electrical, that is the potential difference, can be easily calculated. This helps us to know the positive. That is, from the galvanometer, we can find out the positive and the negative terminals by the flow of the current, because electron flow is in the opposite direction. So here an example can be taken. You can take an example, that is, we are going to find out the standard electrode potential of zinc electrode. That is, we want to find out zinc in zinc sulfate solution. It is dipped, and you are going to find out the electrode potential of this half cell. Zinc electrode containing 1 molar concentration of Zn2 plus ions is connected to SHE. So zinc is dipped in 1 molar concentration of Zn2 plus ions and is connected to the standard hydrogen electrode. The voltmeter reading shows a potential difference. That is, as I told you earlier, the potential difference can be calculated. Once it is connected, the potential difference, the EMF, is found to be 0.76 volt. The E cell, or the cell voltage, was found to be 0.76 volt. The electron flow was found to be, from the galvanometer, the electron flow was found to be from zinc to SHE. So that shows that zinc is acting as an anode and SHE is acting as a cathode. So the Zn plus 2H plus ions gives Zn2 plus plus hydrogen, because zinc is getting converted to Zn2 plus and H plus is gaining electrons to liberate hydrogen. So here, as we know, the cell voltage is equal to E naught of cathode minus E naught of anode. Now here, cathode is the hydrogen, SHE, and anode is the zinc electrode. So cathode is 0, 0 minus, it is the anode part. We don't know. E naught of Zn2 plus slash Zn we don't know. So E cell is 0.76. So 0.76 is equal to E naught of cathode is 0. 0 minus the electrode potential of zinc. So we get the electrode potential half cell value, reduction potential of Zn would be equal to 0.76 volt. Similarly, when copper in copper sulfate is coupled with standard hydrogen electrode, there copper will act as a cathode and SHE will act as an anode. And from the potentiometer, we can find the potential difference, and potential difference E cell, or cell voltage, is equal to E naught of cathode minus E naught of anode. Here the cathode part is copper and anode is the SHE, and SHE is taken as 0. So from the potential difference, we can calculate the half cell, that is copper in copper sulfate. So this is how we calculate the electrode potential of every half cell.